Hello, students. So where do we stand? How have we gotten any closer to actually solving the original question we wanted to about this game, which involved permuting these blocks here? Well, what I'm going to need is what have we done? Well, we've defined this thing called the alternating group, and this ends up corresponding to the actual positions that you could get from having the blocks in order. Every possible element of that group is equivalent to one move in this game that we made. Okay, so we've seen that. We haven't determined the size of these alternating groups yet, but there is one result that I need to tell you about, which is that the identity, which we showed was in the alternating group, thankfully, otherwise it wouldn't have been a group, the identity cannot be written as an odd number of 2 cycles. Now, this is proved in an undergraduate class in group theory. What I'm trying to do here is I'm trying to give you sort of a crash course in group theory, and this proof is kind of long. I shouldn't say this proof. There are 2 proofs that I really like of this statement, and whenever possible I show my students both. There's one that involves matrices and linear algebra, and you take a determinant and it's beautiful. Everything works out. It's a gorgeous proof. If you haven't seen it yet, it's something to look forward to. But I don't have time to prove this here. But we are going to accept it. It's a true statement, and I promise you, there's more than one very nice proof of this in an undergrad class. So accepting that the identity cannot be written as an odd number of 2 cycles, we now want to make the following claim, that every element of Sn is either an odd number or even number of 2 cycles, but not both. Okay, there's 2 parts to this. 2 parts here. One is I'm claiming that every element of the permutation group, of the symmetric group or permutation group, happens to either be writable as an odd number of 2 cycles or an even number of 2 cycles. So you can get to any permutation with just a product of 2 cycles of some length. But this is now claiming that every element is either an odd number or an even number, but not both. You can't have a permutation that you could reach both ways. You could either reach it with an odd number or you could reach it with an even number. Okay, so we actually are going to prove this. The first part's actually quite easy if you realize something. If I have a cycle, A1, A2, A3 to AN minus 2, AN minus 1, all the way up to AN. I want to show that any cycle can be written as a product of 2 cycles, and we know that any permutation can be written in terms of cycles, disjoint cycles. So as long as I could write each of these cycles as some number of 2 cycles, I don't know what that number is, but as long as I can do that, then I can write any permutation as a product of 2 cycles, because I could go cycle by cycle by cycle in order to do this. So how could I write this as a product of 2 cycles? Well, what I'm going to do is I'm going to do this. AN minus 1, AN, AN minus 2, AN. Well, the next one would be AN minus 3, AN, all the way down to A3, AN, A2, AN, A1, AN. Squeeze that in there. Okay, so how do we do this? Well, we just check. Where does this take A1? Well, this takes A1 to AN, and this takes AN to A2. And each of these, no more A2s appear. So this product of 2 cycles takes A1 to A2. Well, look, so does this. Okay, where does this take A2? Well, this doesn't move A2 at all. This moves A2 to AN. This moves AN to A3. And there's no more A3s appearing, so this moves A2 to A3. So as we keep going, we go from number to number to number, and we see each of these travels to the next one. Now, what about AN, though? Let's check that. Well, AN goes to A1, and there's no more A1s. So AN does go back to A1. So this is the same as this. So this shows me that every cycle can be written as a collection of 2 cycles, which means every permutation can be written as a collection of 2 cycles. So since every permutation can be written, well, that means it can be written as either an odd number or an even number of 2 cycles. We just don't know which. Now, the other one is the both part, right? So suppose there's some permutation that can be written as both an odd number and an even number of 2 cycles. So let's say we call it, I'll call it just x. No, I don't want to do that. Let's use sigma. So let's say this is both an odd number and an even number of 2 cycles. So I'll say this is A1, A2, A3, so on through A2n, and it's also equal to B1, B2, all the way through B3, all the way up to B2m plus 1. Okay, so we have some permutation that can be written as an even number of 2 cycles, and an odd number of 2 cycles. And we're assuming that all the A's here are 2 cycles and all the B's here are 2 cycles. So these are 2 cycles and these are 2 cycles. Okay? So now what do we conclude? Well, I actually don't care about this sigma. I don't care what it is. I only need to work with this from now on. Because what could I do? Well, I know that the inverse of each of these elements is itself. The A1 times A1 is the identity. A2 times A2 is the identity. The inverse of a 2 cycle is itself, because if you reverse the 2 elements, well, it doesn't matter what order you put them in, right? Because we can rewrite. We don't have this uniqueness of appearance here. So each of these are their own inverse. So what I could do here is I could multiply both sides on the right by A2n, and then A2n minus 1, and then so on and so forth, all the way down. So what that's going to give me, so I'll have on the right, I'll have B1, B2, through b to the 2m plus 1, and then I'll have a2n, a2n minus 1, all the way down to a3, a2, a1. Okay, on the right. But if I multiply on the right by a2n to a2n minus 1, and so on, well, when I multiply on the right by that, this goes away, and then the next one goes away, and then the next one goes away, all the way till there's nothing left. When I end up with an a1 left on the left, and then when I multiply both sides by a1, that a1 goes away, and I get the identity. And lo and behold, see what happens here? How many different 2 cycles do I have? I have 2m plus 1 plus 2n, because I have all of the b's and all of the a's. So this is 2 times m plus n plus 1, which is odd. By the very definition of odd number, this is something of the form 2k plus 1, therefore it's odd. Now our assumption was that the identity can't be written as an odd number of 2 cycles, so we know that if there were any permutation sigma that could be written both as an even number of 2 cycles and an odd number of 2 cycles, then we would be able to write the identity as an odd number of 2 cycles, which is a contradiction because our assumption is that we cannot. So that's how that argument works. So that's important, that every element is either even or odd. And I'm going to now refer to permutations as being even permutations or odd, because that's just a shorthand. Instead of saying this permutation can be written as an even number of 2 cycles, I'm going to say this permutation is even, much shorter. And if instead of saying this permutation can be written as an odd number of 2 cycles, I'm going to just say this permutation is odd. Now this statement says that E is not odd. And AN is just a collection of even permutations. Now, there's much more to say, and we will keep looking at this AN as we move on.